Hello again. In this video, we're going to go over section 2.6, part 2, which is about continuity. Now, in the last video, we talked about continuity at a point. And so just as a reminder, the definition of a continuity at a point says a function f is continuous at a if the limit of f of x as x approaches a is equal to f evaluated at a. And there's this continuity checklist that you can use to determine whether these are equal. And it consists of checking that f of a exists and is defined as a number, and also checking that the limit of the function exists as x approaches a, and then making sure that those two numbers are equal. Okay, so what I want to do here is look at example 2 and determine whether these functions are continuous at a. And we're going to refer to the continuity checklist to make that determination. Okay, so for this function here, let's try to determine whether it's continuous at a is equal to 1. And going through the checklist, the first thing that we have to determine is whether f of 1 is defined. But notice if you plug a 1 into this, you actually get 6 divided by 0, and of course that's undefined. Okay, so this is not continuous at 1. Because it doesn't satisfy the first condition on that continuity checklist. Okay, remember, the function needs to be defined at the a value, and in this case it's not. Okay, but if we change it to a different value, so let's check continuity at a is equal to 2, let's see if it's continuous at 2. Okay, so f of 2, let's see what that's equal to. When I plug a 2 into this function, on top, it looks like we get 12 plus 4, which is 16 plus 1, so that's 17. And on the bottom, of course, you just get 2 minus 1, which is 1. So f of 2 is equal to 17. So it's defined at 2. Then we have to check the limit of the function as x approaches 2 and make sure that it exists. Okay, so there's various ways of calculating limits. You could create a table or you could look at the graph. But in this case, let's go ahead and use substitution. And we know we can use substitution to evaluate this limit because it's a rational function where the denominator is not equal to 0 when you use substitution. Okay, so if you plug 2 in, of course, you get 17. So by direct substitution, I know the limit of this function as x approaches 2 is 17. Okay, and then part 3 is these would have to be equal, and of course they are. Okay, so both of these are 17. Okay, so by the continuity checklist, all 3 conditions are satisfied. And so this function is continuous at a equal to 2. Okay, now let's look at this last function. Now this is a piecewise function where the output of this function is x times sine of 1 over x if x is not 0, and it's 0 if x is 0. Okay, so let's run through the checklist and see if it's continuous at a equals 0. Okay, so the first thing is we need to make sure that h of 0 is defined. But of course it's defined. In this piecewise function, if x is 0, then the output for this function is 0. So it's defined. The second condition is we need to check the limit of this function as x approaches 0. Now notice as x is getting closer and closer to 0 here, the output for this function would be x sine of 1 over x. And we showed in a previous video that the limit of that function as x goes to 0 is actually equal to 0. And we did that using the squeeze theorem. And so I'll just quickly show you how we did that. We first started with this idea that the sine of 1 over x is trapped in between -1 and 1. And then we multiplied all three sides of this by x. Giving us this compound inequality. All right, and then using the squeeze theorem, we showed that as x is heading towards 0, obviously this is heading towards 0, and so is this. And so the squeeze theorem says, well, if that happens, then this function must head towards 0 as well. Okay, so we know the limit of this function. Using the squeeze theorem, we know the limit of this function as x approaches 0 is 0. Okay, so this limit exists, and of course they're equal, and so the third condition is satisfied as well. Okay, so yes, it is continuous. H of x is continuous at a equals 0. Okay? So these are just some really nice examples of showing you how you can apply the definition of continuity at a point to determine whether a function is continuous at a specific point. Okay, and I recommend using the checklist. Just make sure you check all three conditions. Okay, so let's go back and talk about the next theorem. So theorem 2.9, we have some rules for continuity. So if f and g are continuous at a, then the following functions are also continuous at a. Now we're assuming c is a constant and n is a positive integer in this case. So if f and g are continuous at a, then if you say f plus g and form that new function f plus g, that's also continuous at a. Also, if you say f minus g is also continuous at a, as long as f and g are continuous at a. You can multiply a function by a constant, and it will remain continuous at a. You can multiply f and g together, and it will remain continuous at a, as long as f and g are continuous at a. You can divide them, so f divided by g is still continuous at a, provided that g of a is not 0, because if g of a is 0, then this would be undefined. And then if you take a function and raise it to the nth power, again, remember n is a positive integer, then it remains continuous at a, as long as f is continuous at a. So these are some nice little rules for continuity. Okay, and that leads us to theorem 210, which tells us that polynomial functions are continuous for all x values. Now that should be fairly clear if you're familiar with the graphs of polynomial functions. Polynomial functions simply go up and down in a very smooth way. And so you can draw a polynomial without having to lift up your pencil at any point. And so therefore it's continuous at all points x. Now rational functions in the form of p over q, where p and q are polynomials, that's the definition of a rational function. Okay, they're continuous for all x values for which q of x is not 0. And notice q q of x is this bottom polynomial, the one in the denominator. And again, the issue there is if q of x is equal to 0, then this function is not defined because you're dividing the top polynomial by 0. Okay, but as long as q of x is not 0, then this function is, rational functions are continuous for all x values. Okay, except the ones where you get q of x to be 0. Okay, so let's try to apply this theorem to example 3. Okay, so for this function, we're going to try to determine where this function is continuous. Okay, so according to the previous theorem, since this is a rational function, right, this is a polynomial divided by a polynomial, the previous theorem said that rational functions are continuous at all x values where the bottom polynomial is not equal to 0. So let's set the bottom to 0 and find out which x values make this denominator equal to 0. Okay, so to find this, of course, you would want to factor this. Okay, and this would factor into x minus 3, x minus 4. And then when you solve this, you get x equals 3 or x is equal to 4. Okay, so there's two x values where the denominator of this function is equal to 0, right? 3 and 4. And so according to the theorem, this rational function is continuous at all x values except for these two. Okay, and so we'll say it's f of x is continuous everywhere except that x equals 3 and x equals 4. Okay, by the previous theorem that we just looked at. Okay, and if you were just curious, you could graph this function and you can see what's happening at x equals 3 and x equals 4. You actually have asymptotes at these points. And so our intuitive sense of continuity, you can see, you can draw this function over here without lifting up your pencil, so it's continuous everywhere over here. But you do have to lift up your pencil at x equals 3 to draw the rest of it here. Now it's continuous at all x values in here, but then you have to lift up your pencil at x equals 4 to draw the rest of this function over here. Okay, so the graph supports our conclusion that we found. Okay, so I hope you found this video helpful. In the next video, I'll continue to talk about some of the material from 2.6, and hopefully you'll get a chance to look at that one as well. Thank you for watching. Bye-bye.